Welcome back to Integral Calculus. In this video, I'm going to be talking about natural logarithms. Before I can get into that, there's a little bit on the business end I have to talk about. Normally, I try to keep these sorts of things out of the lecture videos, but in this case, it is important. In the United States, there is a great culture war amongst mathematics educators about how to teach calculus. The old guard teaches what is called late transcendentals calculus, and that's the style that these videos are based around. The other style is called early transcendentals calculus, and it's used predominantly in support of engineering programs and other programs where they're going to try to build on statistics in cramming entirely too much math into an undergraduate education in too short a period of time. Right. So the transcendental functions include the trigonometric function, the logarithmic functions, the exponential functions, the inverse trigonometric functions, and the hyperbolic functions. In the early transcendentals sequence, the class generally assumes that you're familiar with all of these, except maybe the hyperbolic functions. Coming into the class, we're just going to dump a bunch of definitions on you and we're going to move on. In the late transcendentals class, we want to spend a little bit of time exploring how and why some of the differentiation and integration rules came about. And in order to do that with the logarithm and the exponential functions, we have to have developed a pretty extensive background in derivatives and integrals. I bring all of this up because if you happen to have taken your first semester calculus somewhere other than here, if you happen to have taken your first semester calculus somewhere other than here, and you came from an early transcendentals program, then you're going to feel like I'm acting as though you haven't seen things that you're very familiar with. I ask you to play along and try to follow along anyway, because I think that the insights are worth it even if you know what the end goal is. With all of that said, let me get my head out of the way and let's dive into this. We start with the power rule for integrations, which says that the indefinite integral of x to the m dx is equal to 1 over m plus 1 times x to the m plus 1 power plus some constant of integration. And the problem here is that when m is equal to -1, then all of a sudden you have 1 over 0, which is undefined. So the power rule is only defined when m is not equal to -1. In the elementary integrals that you learn about in the first semester of calculus, there is no rule for x to the -1, which is 1 over x. And so we want to address that problem. The way we're going to address it is to just force it. Let's invent some new function called L. L of x is going to be the integral starting at 1 and going to x of, well, I guess we can't do 1 over x, so we'll create some sort of a dummy variable to fill in, right? X is already defined outside the integral, so the variable inside the integral should have some other name. I like using the Greek letter tau. I've seen other Greek letters. I've seen people use T. I've seen people use U. It doesn't really matter. You need to fill in with something. so that you can integrate that thing, and then you'll be fine. Now, by the fundamental theorem of calculus, the derivative of this new function L of x is 1 over x. And so from there, an antiderivative of 1 over x would be this new function L. And then because indefinite integrals need a family of functions, you can add any arbitrary constant to that and get a new one. Now that we've defined this new function, we should start to investigate it a little bit. The first thing that I want to notice is that if you take this new function and evaluate when x is equal to 1, well, the definition says it's going to be the integral from 1 to x, in this case x is 1, of that 1 over variable with respect to that variable. Again, I like tau. If you don't like tau, you can use something else. But we're taking an integral where the upper and lower limits of integration are the same number. And a nice property of integrals says that whenever you're integrating from a to a of anything, you get 0. Second property. Well, what happens at 0? This is probably the strangest of all of these. Well, it'll be the integral from 1 to 0 of 1 over tau d tau. And that's kind of weird, starting at the larger number and going to the smaller number. So remember the property of integrals that says you can switch the limits of integration by putting a negative sign in front. So this is the same thing as the negative of the integral from 0 to 1 of 1 over tau d tau. Although I'm not entirely sure that that helps all that much, we can think about this graphically, right? An integral is the area underneath the curve that is the graph of the function. And so maybe we will think about the reciprocal function, whose graph looks something like that. And then the area in question is this sliver here. But the reciprocal function goes to infinity as the variable, tau in this case, goes to 0. And unfortunately, the area underneath an infinitely tall curve is going to tend to infinity as well. But we've got a negative up here. So I guess we can say that L of 0 is going to tend to negative infinity. Either way, it's a pretty good sign that there's going to be a vertical asymptote in the graph of L of x at the point when x is equal to 0. All right. So analyzing graphs, we're generally looking for x-intercepts and y-intercepts. Well, we found the x-intercept, 1, 0. We tried to find a y-intercept and found that the function isn't actually defined when x is equal to 0, so there is no y-intercept. Along the way, we found a vertical asymptote. Then the next step is to take a look at the first derivative test, look for ranges where the function is increasing or decreasing, look for any extreme values. So we'll take the derivative of L of x, and we will get 1 over x. Now we know when x is equal to 0, this function is undefined. When x is greater than 0, the derivative will be greater than 0. Which means that this function is monotonically increasing. You should notice here that I'm making a choice. There is nothing in what we've done that should force x to be greater than 0. But it will turn out that that's actually kind of useful. Very specifically, we're going to want this function to have an inverse. And if we choose to ignore the branch when x is negative, then this monotone increase will be enough to ensure that the function has an inverse, and we'll be happy. All right. So with that in mind, let's continue onward. One more property I want to look at. If it's monotonically increasing, there are no maximum or minima. But we can also think about the concavity. Well, to think about the concavity, we need the second derivative. If the first derivative is 1 over x, the derivative of 1 over x is negative 1 over x squared. Negative 1 over x squared is negative for any x except x equals 0 where it's undefined. Because of the branch choice I made before, well, I'm only going to care about what happens when x is bigger than 0. But the important thing here is the function is going to be concave down. All right. Because the function is monotonically increasing, chances are good, but not guaranteed, that there will not be a horizontal asymptote. I guess I should check that. I'm not going to bother writing it down, but it's going to be kind of the same argument we used up here for number 2. If you want to look at, there we go, now I can actually gesture. If you want to look at what's going to happen as x goes to infinity, well, it'll be the area of this part of the curve, the part that's not shaded in the figure up here. And that's also going to be an infinitely large area. So the function is going to go towards infinity as x goes to infinity. There is no horizontal asymptote. All right. So with all of that information, we can draw this graph. We're going to go through the point 1, 0. We're going to have a horizontal asymptote at x equals 0. We're going to increase, and we're going to be concave down. And at this point is when we have to tie things back to things that you have studied before. This is a graph with which you should be familiar. This graph is the graph of the natural logarithm. And so yes, this function we've just invented is a function you have seen before. It is the natural logarithmic function. And we'll generally write that as y equals ln of x. While I expect just from this graph that you should be able to recognize that this is a logarithmic curve of some sort, it's not entirely clear immediately that it's going to be the natural logarithm. We'll get into why that's going to be the case in a future video. It has to do with just figuring out what happens when y is equal to 1. But for right now, we have a couple of fairly straightforward rules that we've now established. Because our function is the natural logarithm, then just using the same rule we just established, the derivative of the natural log of x is 1 over x. And then applying the chain rule, the derivative of the natural log of some function u of x would be 1 over u of x times the derivative of u of x, u prime of x, which we generally write as just u prime over u because we're lazy and of x is too much to write out. And then finally, the integral of du over u is going to be the natural log of u plus c. Although here I have to pay back that shortcut that I took earlier of insisting we only care about the horizontal or the positive branch. There's no reason we couldn't deal with the negatives just as well, and so we have to include those in here. And we're going to do that just by mirroring the function and taking the natural log of the absolute value of u. These rules are fairly straightforward. I don't think I need to go through an example before I give you one to try. So let's just dive in. And I would like you to take the derivative of the natural log of 3x plus 1. Take a couple of minutes, see what you can do with that one, and I'll see you in the next video.